Hello, everyone. My name is Zhang from University of Bristol. I'm pleased to present our work on enhancing VMAF through new feature integration and model combination. This work is based on the collaboration between Netflix and the University of Bristol. In recent years, the consumption of video data has increased significantly, in particular with the impact of the COVID-19 pandemic. For video service providers, video quality assessment is a key tool which can enable them to accurately estimate the quality of a streaming content and improve user experience. Video quality can be assessed through psychophysical experiments, which are effective but also costly and time-consuming. That is why much more efficient objective quality metrics have been developed to achieve good correlation with subjective opinions. The most commonly used quality metric is PSNR, peak-to-signal noise ratio. It simply measures the pixel-wise distortions between the test content and its reference counterpart. However, it does not always correlate well with visual perception. In the past 2 decades, many perceptually inspired objective quality metrics have been proposed, targeting enhanced correlation with subjective quality compared to PSNR. Among all these approaches, one of the most successful examples is the Video Multi-Method Assessment Fusion Approach, VMAF, which was developed by Netflix. VMAF combines 6 different video feature and metrics using an SVM regressor and was trained on a large HD video quality database, VMAF Plus. Although VMAF has achieved a consistent improvement over PSNR and other perceptual quality metrics, we notice that VMAF only includes one temporal feature based on frame differencing, and this can lead to inconsistent performance for content with a complex temporal activity. Additionally, the training database VMAF Plus only contains test sequences generated by an 8264 codec and the resolution resampling, which cannot be guaranteed to achieve optimum consistent performance when used on content compressed by other video codecs. In this context, we have proposed the following enhancement solutions. We have first enhanced the ADM metric, which is the most important feature in VMAF, by integrating a feature related to dynamic texture. We have also trained 2 SVM models based on selection from a pool of original VMAF and the new features. The final quality index is then obtained by linearly combining these 2 models, where the training is based on 2 different databases. The new approach has been evaluated comprehensively on 8 HD databases and benchmarked against the original VMAF and other popular quality metrics. Before we introduce the proposed method, I would like to summarize the databases we have used in this work for training and testing. In this work, we have used 10 HD databases in total. The number of source and test sequences and their primary features are listed in this table. In this work, we solely focus on the content with artifacts due to compression and resolution resampling. We have therefore removed the test versions with other distortions, such as transmission errors. We have then calculated the ranking correlation coefficients of the original VMAF on these databases. And you can see that VMAF performs really well on most databases, especially on those which are similar to VMAF Plus dataset. However, the performance of VMAF is relatively low on some databases, including MCLV and CCHD. In this work, apart from VMAF Plus database, we have used an additional training dataset, CCHDDO, due to its diverse source content and distortion artifacts. And the other 8 databases will be used for testing. The proposed approach is illustrated in this slide. It first calculates a modified ADM index based on the input reference and the tester video frames. The modified ADM is then combined with the other 5 original VMAP features, including the frame difference, 4 VAF values at different scales, and the new selected features using an SVM regression model trained on the VMAF Plus database. An additional SVM model was trained based on new selected features and the second training dataset CCHD-DO. Both model outputs are then combined using a normalized linear model to generate the final quality index. This slide shows how we modified the original ADM metric. ADM predicts perceptual quality through separately estimating detail losses and additive impairments. The figure on the right in this slide shows the workflow of calculating ADM. We noticed that in the original ADM calculation, it exploits 2 human vision system characteristics, contrast sensitivity and spatial masking. However, it does not fully capture temporal masking effect due to dynamic textures, such as water, smoke, and steam. Therefore, we have modified the contrast masking thresholds MT lambda in ADM by integrating a dynamic texture feature, DTF lambda. This feature is based on the displaced frame difference after motion compensation. The motion compensation operation is performed using optical flow approach in this work. The new masking thresholds MT lambda new replaces the original threshold in the modified ADM calculation. By doing that, we can improve the overall correlation performance of ADM when tested on 10 video databases. The average stroke value increases from 0.8281 to 0.8389. In order to achieve improved correlation performance, new feature candidates alongside the original VMAP features are computed. These include popular quality metrics and the video features as summarized in this slide. These features are calculated separately on Luma and Chroma channels and at 4 different resolutions. These results in a total number of 165 new features. The detailed definitions of these features can be found in our paper and also in the related references. During feature selection, we followed the approach described in this slide, which is similar to the sequential forward method selection in the literature. We also used the Spearman rank order correlation coefficient as the performance measurement. For SVM Model 1, the initial feature set includes the original 6 VMAP features with ADM metric replaced by the enhanced version. The model was trained on the VMAP Plus dataset. For SVM Model 2, the initial feature set is empty. The model was trained on the CCHD-DO database. The new selected feature sets for 2 SVM models are listed in this table, where M1 corresponds to the extension of the original VMAP, and M2 is the second model based on the new selected features. Here, the feature notation tells what is the feature name, on which color channel, and at which resolution scale. The frame level outputs from the 2 SVM models are then linearly combined to generate the final quality index following this equation. To test the performance of the proposed method, as I mentioned, we have used 8 databases which are different from those 2 training datasets. For comparison, 8 other popular quality metrics have also been tested on these databases. These are PSNR, SSM, MSSM, VAF, VSNR, ADM, the original VMAF, and ST VMAF. The performance of all these metrics was evaluated using the Spearman rank order correlation coefficient, and a significant test was also conducted to identify the difference in performance between the original VMAF and other tested metrics on all test databases. We have also conducted ablation studies on our three primary contributions: ADM modification, new feature selection, and the model combination. We also noticed that when quality metrics are employed in practical applications, it is useful to compare a performance of a distorted video sequences generated by different codecs and coding configurations. We have therefore calculated the subjective MOS difference between every pair of test sequences in each of the 8 test databases. When computing the MOS difference, we artificially change the order to ensure that MOS differences are equal to or greater than 0. These results in MOS difference scores corresponding to more than 100,000 test sequence pairs. We have then computed the quality index difference between the test sequences in every pair following the same order for performance evaluation. This table shows a summary of a performance comparison between the proposed approach and the other 8 benchmark quality metrics. For each evaluated quality metric, the SROC value on each dataset is presented alongside an aggregate SROC value for all 8 databases. Each SROC value is followed by a number in bracket, which stands for the significance test result. We can see that in the table, the proposed method offers the highest aggregate SROC value among all tested quality metrics. The improvement has also been achieved over the original VMAF 0.6.1 for all 8 tester databases, and the result is statistically significant on the Netflix dataset. Moreover, according to the ablation study results, all 3 primary contributions have led to higher overall correlation performance when compared to their tested replacements. Among them, the newly selected features contribute the largest improvement. The figures in this slide shows the distributions of the quality index difference values for the original VMAF and the proposed method for all 8 datasets and 3 individual ones. We have also calculated the accuracy ratio for both metrics, which is defined as the number of pairs where the VMAF difference values provide the same classification results as the MOS differences. We can observe that the proposed approach offers a higher accuracy ratio compared to the original VMAF for all data and individual data sets. The overall improvement is 1.4%, which represents an additional 1,440 video pairs that have been correctly classified. This improvement is significant according to statistical test. In conclusion, in this work, we have proposed an enhanced version of VMAF based on dynamic texture feature integration, additional feature selection, and model combination. We have trained and evaluated the proposed method on 10 HD subjective databases. The new approach shows consistent improvement over the original VMAF model on all tested databases. Regarding the future work, we will focus on more challenging cases when multiple codecs and various coding configurations are employed, and also developing more advanced spatial and temporal pooling algorithms. In the end, I would like to thank our research collaborator, Netflix, for their help and support, and also the funding partially from Leverhulme Trust. Thank you very much for your attention, and now I'm happy to take your questions.